screen right now, but I'm hoping you can. So right now, group 1, these all have what in common? Who can tell me? Who remembers? It's very simple. All these have one valence electron. Okay? All these have 2 valence electrons. Okay? 3, and then you jump over to here. 3 valence electrons, 4, 5, 6, etc. Okay? So these guys here, 17, these all have 7 valence electrons, then you get to a full shell. So hydrogen has 1, helium has 2, boom, full shell. Come here. 1, 2, 3, 4, 5, 6, 7, full shell. Okay? Now we go to the third layer. 1, 2, 3, 4, 5, 6, 7, 8, full shell. Jump down. 18. There's 18 going across. Okay? So it's very simple to see once it's explained to you. That's how it's divided, and then it all makes sense. So why is this chunk missing? Because this row only has room for 8 valence shells, or 8 valence electrons. So there's a gap in the table. So you know that these, in your periodic table in your textbook, these are all metals, okay? Alkali metals, alkali earth metals. These are all your transition metals, okay? Then you get into here, and you get your non-metals, and then your noble gases, okay? So today we're going to talk about ionic bonds, and that is between metals and non-metals, okay? So the easiest way to think of it is they all want to fill their shell, okay? So any one of these here, if they're going to combine with one other atom and only one other atom of one type, which one are they going to look for? They're going to look for one in this column, okay? So lithium and fluorine can go together, one of them and one of these, and it's full, okay? 1 sodium, 1 chlorine, table salt, NaCl, it's full. If you go to something like magnesium, magnesium has 2 valence electrons, so magnesium and sulfur makes a full thing, okay? I hope that kind of makes sense, but if they want to combine with other ones, then you might need more than one, okay? And we'll get to that after. But if you look at the valence electrons and what they're trying to do, they are the most stable when their outer shells are full, all right? So let's go back to this now, okay? So the combining capacity, we're going to look at the charge of each element, okay? So we'll use hydrogen for example. Now, if you Google or look up periodic table with charges, you can print one out. And what it does is it shows you your little element. It's got 1, it's got the weight, which is 1 and something else. Let's look at it here. 1, the weight is 1, okay? So there, that's your hydrogen. What it'll have in the top corner is it'll say +1, okay? That's the charge. So that helps in determining the combining capacity, because when you see the charges, you want to make them neutral, which is 0. So if you have +1 and -1, that evens out. But if you have +1 and -2, then what are you going to need? You're going to need 2 of the hydrogens, okay? So we'll use our classic example again is NaCl, okay? I like using water for covalent. I like using salt for ionic, okay? So classic NaCl. So Na is number 11 on the periodic table. It is in group 1, so we know it has 1 valence electron. So its charge is what? It's going to be +1. All these ones have the charge of +1, +2, okay? And it has to do with the valence electron. Why is it +1? Okay? Someone might ask the question, why is hydrogen +1? Why is sodium +1? Okay? It's +1 because hydrogen has one electron to give away or to gain. Okay? So if you look at it, whatever relationship happens, so fluorine is going to receive, it's going to take, well, I don't think that's low enough. Fluorine is going to take an electron. So if it gets an extra electron, it becomes negative. Okay? Lithium has an extra one to give. If it gives one away, it becomes positive because there's more protons than electrons. Okay? So you always got to look at the charges. So these have one to give away. If they give an electron away, that means they're positive. If these ones are all receiving electrons, that means they are becoming positively charged or negatively charged. They gained an electron, so now they have more electrons than protons, making them negatively charged. Some of these in the middle, they're called crazy cousins. They can have more than one charge. They can combine with different ones. Copper can be +3 and +4. There's different ones, okay? Tin, zinc, those ones can have multiple combining capacities, okay? So if we go back to our example, NaCl, sodium, our charge is +1 and chlorine is -1. So if we draw it out, sodium is 11 and chlorine is 17. Yeah. Sodium is 11. Sodium is 11 and chlorine is 17. Okay? So that means sodium has 11. So if we draw sodium, Na, it has 2, then it has 8, then it has 1. Right? And if we draw chlorine, it has Cl, it has 2, then it has 8, then it has 7. Okay? So what's going to happen? This one is going to take this one and it's going to give it to this one here. So now this one will become 8. That will fill its outer shell. This one's going to lose this shell completely and it's going to be full. So by losing one here, this goes to -1, or +1, sorry, because you took the electron away. When you add an electron or a negative over here, it becomes -1. So one of these and one of these, 1 from 1 equals 0. If it's neutral and balanced, it's happy. That's what it wants. Okay? So ionic is always transferring the charge. The charges are transferred. So they're going to pair up. Okay? So another example of this, and I'm going to show you I'll erase this. Another example of this is aluminum oxide. Aluminum oxide. Okay? I like this one. Aluminum. Okay? Aluminum is number 13. 13 and 8. So 13 and 8. So, aluminum oxide. Now, if we wrote down the formula, it would be Al2O3. Okay? That we're going to do after on naming, but Al2O3 is the formula for aluminum oxide. Okay? And we know the periodic table. So now let's just draw our board diagrams quickly. So 2, 8, and 3. And this one here is 2 and 6. Is that correct? That's 13, right? So this has a charge of this has a charge of, it's got 3 to give away, so yeah, +3. And this one has 2 to accept, right? It needs to take 2, so it's -2. That's oxygen, that's aluminum. 2, 6. Okay? So because that's 6, it has room for 2 more in its shell. So now when you look at this, the easiest way I think of it is, how can we get that to equal 0? Well, 2 and 3, what's a multiple that would work? Right? Well, it would be 6. A common divisible or a common multiplier for those would be 6. So how do you get 6 aluminums? Or this number to be 6? If one of them is 3 and you had 2 of them, then this would be plus 6. And if you had 3 oxygens, you would have negative 6. 3 times negative 2 equals negative 6. Okay? So now we have a balanced equation. So that's why it's Al2O3. And the easiest way to think of it is we have a thing called hook ball diagrams. So if you take your charge, okay, aluminum has plus 3. So what it means is it has 3 hooks to fill. Okay? Now, oxygen has negative 2. So oxygen has 2 hooks. Now, I don't draw them coming off the same side. I draw them like that. Now, if you did this, well, what do we do here? Now we have another oxygen and only 1 hook. Well, what about this hook? You can't have an empty hook. Okay? So if you do this, now you have to add another aluminum. Add a hook. Now this one has 2 empty hooks. What do you have to do? Add another oxygen. 2 hooks off the oxygen. Now they're balanced. So how many do you count? 1, 2, 1, 2, 3. A nicer, cleaner way to draw it is like this. Al, 1, 2, 3. Al, 1, 2, 3. Oxygen, 1, 2. Oxygen, 1, 2. Oxygen, 1, 2. Okay, there is a hook ball diagram.